Hello and welcome to day 4 of Jamb Physics in 40 Days. Jamb Physics in 40 Days is a series that is brought to you by Oyalen, where we believe that when you dedicate within 30 to 45 minutes of your time daily, you will be able to get all the skills and tools necessary for you to ace Jamb Physics. So if you're a candidate who is preparing for the Jamb exams and physics is one of the subjects you have chosen in your subject combination, then this video is definitely for you. So please do check it out from day 1 till this very video. We have done well to look at some topics from day 1, day 2 and day 3 which you do not want to miss. And please ensure that you like the videos, share them amongst your friends and also subscribe to the channel. Now, day 4 is about the gravitational field. Now, here are some of the subtopics that we have in gravitational field that JAMB expects that every candidate should know about. So the first thing, you should be able to state the Newton's law of universal gravitation. This is when you're expected to know that when you have two massive objects separated by a distance r, the force of attraction between them is given by this equation where F is G m1 m2 over r squared, where F here stands for the force of attraction, G here is the universal gravitational constant. It is 6.66 times 10 raised to the power minus 11 in magnitude. And then m1 is the mass of object 1, m2 being the mass of object 2, and r is the distance separating them. You should also know about the gravitational potential, which is given as negative Gm over r. So gravitational potential is denoted V, and this is equals to negative G, also the gravitational constant, m being the mass and r being the radius in this case. You should also be familiar with conservative and non-conservative fields, as well as acceleration due to gravity. Then you should also be able to solve problems that involves the variation of acceleration due to gravity on Earth's surface. And you should tell the difference between mass and weight, where mass is the amount of stuff that an object possesses, denoted m. And then weight is the product of that mass and the effect of Earth's gravitational pull, known as G. So weight is mg. And then you should also be able to calculate escape velocity, which is given as v equals the square root of 2gr. And then finally, you should be able to explain parking orbit and weightlessness. Now, these are the subtopic on this the topic of gravitational field, and we'll be solving some questions that JAMB has set in the time past on each of these subtopics. So as we do these calculations, please get your materials ready and follow learn. And if you have any question, please ensure that you put it into the comment section and we'll definitely attend to all your questions. This question from the 2006 UTME says, if the radius of the Earth is 6.4 times 10 to the power of 6 meters, the escape velocity of a satellite from the Earth is... So to find escape velocity, we have to recall the equation for this. So V equals the square root of 2gr. Remember, this G is gravitational acceleration, while r here is the radius of the Earth. Now please take note, when you're writing capital R like this, that is for radius of the Earth. But when you want to look at two distance between objects, we just use that as small letter r. So please, if you see big R, that's radius of Earth. So let's solve. V therefore becomes the square root of 2 multiplied by gravitational acceleration, that's 10, multiplied by the radius of the Earth, 6.4 times 10 to the power of 6. Now, when you compute this, you find that V equals 11,303.7 meters per second. But the options provided here are in standard form. So let's bring this to standard form. V would then be, now take the decimal point 1, 2, 3, 4 places. That is 1.13 times 10 raised to the power 4 in meter per second. So the correct option is option A. This 2010 UTME question says, a stone and a feather are dropped from the same height above the Earth's surface. Ignoring air resistance, which of the following is correct? So we are asked to look at these observations here and see which one of them is correct with this statement here. And please take note, we are told to ignore air resistance. Now, the first statement in option A says, the feather will be blown away by the wind while the stone will drop easily. Now, this is what will happen when air resistance is factored in. But in the question, we are asked to ignore air resistance, so this is false. B says the stone and the feather will both reach the ground at the same time. And this statement is correct because when you drop two objects, regardless of their mass, what will happen is that they are all going to experience the same acceleration due to gravity, which means they will travel to the ground at the same time. So B is correct. Now, option C says the feather will reach the ground first. Now, this is never correct, whether we ignore air resistance or not. Because if you apply air resistance, the feather will reach the ground last. And if you are ignoring air resistance, they will reach the ground at the same time. So this one is totally wrong. And then option D says the stone will reach the ground first. And that would have occurred if air resistance is being factored. So in all the statements here, the only correct one is option B. So we go with that. The value of x, y, and z respectively in the expression m to the power of x, l to the power of y, and t to the power of z for the universal gravitational constant G are. Now, before I go on to solve this question, if you're yet to be subscribed to the channel, please do so. It's only going to take a second of your time. And when you subscribe, you are helping us to be able to make more meaningful and helpful videos like this. So please do subscribe and hit the notification bell icon so that you get notified every time we put out a new content. So to solve this question, we're going to apply the dimensional analysis. But we're going to start with the equation for the Newton's law of universal gravitation. Now, from the law, we know that F equals G m1 m2 over r squared. Now, working with this, let's make G the subject of the formula. From here, we can then say G equals, now you multiply this, so we have F r squared, and then we divide it by this 2 here, m1 m2. Now, applying dimensions, let's find the dimension of force. Now, to this part here, dimension of force is in ml t to the power of minus 2. Now, we're going to multiply this by the dimension for radius, for length squared, where r is the distance between the two objects. So that is length times length. So we're going to be having L squared here. All divided by, now this is mass. And the dimension for mass is m. So m times m, we have m squared. So let's solve this. From here, we can then have m over m squared multiplied by, now L, we have L times L squared, then multiplied by t to the power of minus 2. So here we're going to be having m power of negative 1. Then this would give us L cubed. And then this would give us t minus 2. Now let's equate it with what we are given here. M power of x, L power of y, and t power of z. So we can see that x equals minus 1, y equals 3, and z equals minus 2. So our answer is going to be minus 1, 3, minus 2. Now let's check the options. Minus 1, 3, and minus 2. That is option B. That's the correct one. An object is weighed at different locations on Earth. What will be the right observation? So let's look at the observation and pick out the one that is correct. A says both the mass and the weight vary. Now this is false because we know that mass is a fundamental quantity and does not change regardless of location at all. It does not also vary with time, so it does not depend on anything at all. It is always constant. And on the other hand, we know that weight depends on gravitational acceleration, which is different at different points on the Earth's surface. So we already know that mass should be constant and weight should vary. So let's see what option B says. B says the weight is constant while the mass varies. This is also false. It should be the reverse case. Now, option C says the mass is constant while the weight varies. Now, this is the correct one. The mass is constant regardless of the location, while the weight varies as you move from point one to another on the Earth's surface. But to do due diligence, option D says both mass and weight are constant. So we know this one is false since we've already agreed that mass is constant and weight varies. So the correct option to pick here is C. The gravitational pull on the moon is 1/6 that of the Earth. So if a body weighs 6.0 Newton on the moon, what will be the weight on Earth? So to solve this, let the weight on Earth be W. So we know that 1/6 of W is what will give us the weight on the moon. So that will be 6.0 Newton. So from here, we can then say the weight on Earth, W, therefore becomes 6 multiplied by 6.0 Newton. And that will give us 36.0 Newton. So the correct option is D. This 2024 UTME question says, the gravitational force between two objects is 10 newtons. What is the new value of the force if the distance between them is halved? So let's solve this. So since we are given the initial force, let's call that F1. And the equation, according to Newton's law of universal gravitation, is G m1 m2 over r squared. And all of this gave the 10 newtons. So what will be the new force, right? So let's call that F2. So F2 will then become G m1 m2 over r over 2 squared. Now this would imply that we would have G m1 m2 over r squared divided by 4, because we have to square everything in this bracket. Now you can solve this based on the law of indices and then take this 4 up here. You then have 4G m1 m2 over r squared. Now if you're observant, you will see this here. That is, F2 is therefore, we can call out this 4. And all of this, what I've just circled here, is actually your F1. So that will be 4F1. So let's calculate the value then. That will be 4 multiplied by, the value of F1 is 10 newtons. So this gives us 40 newtons. And looking at the options, that is option C. The gravitational force between two objects of masses 10 raised to the power of 24 kilogram and 10 raised to the power of 27 kilogram is 6.67 newtons. Calculate the distance between them, taking that a gravitational constant is 6.67 times 10 raised to the power negative 11 Newton meter square per kilogram squared. Now, what we have to use here is to apply the Newton's law of universal gravitation. And when we're going to solve that, we already have all the other parameters except for the distance. So let's solve for distance. The equation itself says F is G m1 m2 over r squared. But from here, we can make r the subject. That will then become the square root of G m1 m2 over f. So let's just apply this, and then r will then be the square root of G, which is 6.67 times 10 raised to the power minus 11. Now multiplied by m1. m1 is given as 10 to the power of 24. Multiply that by m2, which is 10 to the power of 27. All divided by f, which is 6.67. All you have to do is apply your knowledge of indices and you should get this right. So we can say 6.67 divided by 6.67 and that will give us 1.00 times. Now, applying laws of indices to this, we would have 10. Now, we add all this power. Negative 11 plus 24 plus 27. Now, you can add these positives first. This will give you 51. Now, 51 minus 11 will give us 40. So, this will be 40. And of course, r can then be, now, square root of 1 is still 1. So, 1.0 times square root of 10 raised to power 40 would give us 10 raised to power 20. And this is in meters. So the correct option here is option A. A man stands on a spring balance placed in a lift. The lift descends at a constant velocity, and as a result of this, the scale reads a weight. Now we are given 4 options to pick from. Now, before we answer this, let us revise what happens to your weight when you are in an elevator that is either moving upwards or downwards. Now, when you are in an elevator and you are taking your weight, if your original weight is, let's say, weight 1, what happens to your weight when you are now in the elevator? Now, when the elevator is moving upward, at an acceleration A, your new weight will then be greater than your initial weight. Now, when it is coming down at an acceleration A, your new weight would be less than your initial weight. And then when it is moving freely under gravity, your new weight is going to be 0. Now, why this is like this is because your weight in an elevator is given by W equals M into G plus or minus A, where we apply addition when it is moving upward, but subtraction when it is moving downward. And by the time you are moving freely under gravity, the acceleration at that point is equal to G. And when you do G minus G, you get 0. So that is why it becomes weightless at that point. So you might have observed this before, that when you are in a lift or elevator, whichever way you like to call it, when you are in that machine and you are moving upward, you always feel a lot more heavier than you are normally. And when you are coming downwards, you feel like your weight is reduced, right? So this is what happens. It's due to these equations that I've just placed here. Now, let's look at the observations here. A says the weight will be greater than the weight of the man. B says it will be the same as the weight of the man. And then C says it will be 0, while D says it will be less than the weight of the man. But in the question, it is coming down at constant velocity. Now, constant velocity means there is no acceleration. That is, A is 0. So when we plug in 0 to this point, what will happen? You see that the weight will still be mg, which is the initial weight of the man. So the correct option is option B. This question says, the force with which an object is attracted to the earth is called its. Now, this does not only go for earth alone, it applies to every massive object. They always tend to pull other objects around them to themselves due to a force that is created by their gravitational field. And that force is called its force of gravity. So Earth has its own force of gravity, so does every other massive object that we have in the universe. But as far as this question goes, the correct option is C. The force experienced by an object of mass 60.0 kilograms in the moon's gravitational field is 1.002 times 10 raised to power 2 newtons. What is the intensity of the gravitational field? Now, to find intensity, Note that intensity, gravitational intensity is denoted E, and this is equals to F over m, where F is the force of gravitation, right? So applying this, we can then say E equals F is given as 1.002 times 10 raised to power 2 Newton, all divided by, now m, the mass of the object, is 60.0 kilogram. So all we have to do is compute this, and this is going to give us 1.67. So, and the unit is Newton per kilogram. So the correct option is option B. Now this question says, a body is projected from the Earth's surface with the intention of letting it escape from Earth's gravitational field. What is the minimum escape velocity of the body? Then we are given two hints. We are to take Earth's radius as 6.4 times 10 raised to power 3 kilometers, while we are to take gravitational acceleration as 10 meters per second squared. Now, many students, when they solve this question, they tend to hit a problem here. They always use this just as it is, 6.4 times 10 raised to power 3 kilometers, because when they look at the option, they see it in kilometers per second. So they think what they should be solving should also be in that kilometer range as well. But this is the thing. You have to note that gravitational acceleration here is given in meters per second. So if you are going to work with this, and you know from the formula, when you're solving here, you will see that V is actually the square root of 2GR. And it's only when you multiply M by M that you can get M squared for the square root, right? That is what will bring it to meters. So you have to convert this into meters rather than kilometers. So to solve it, we'll then say V equals the square root of 2 multiplied by G, which is 10, multiplied by R. Now this R will then be written as 6.4 times 10 raised to power 6. Now, why is it 10 raised to power 6? Because you have to multiply this by 1000. And when you do that, 1000 is 10 cubed. And of course, 3 plus 3 will give you the 6 that we have here. Now, all you have to do is just compute this, and then it will give you 11,313.7 meters per second. Now, of course, to bring this to kilometer, this will then be 11.3 kilometer per second. And it appears that the options provided has been taken to the nearest whole number. So we'll then take 11 as our answer. So this is approximately 11 kilometer per second. That is option D is the correct one. This question starts with 4 statements. So let's read the statements. 1. The Earth is not spherical but elliptical in shape. 2. Variation in latitude and longitude. 3. Rotation of the Earth on its axis. And then 4. Variation in the density of the Earth. Now the question itself says, on which combination of the above does weight of an object vary on the Earth's surface? So this question wants us to pick out which of these statements actually tells us why the weight of an object vary on the surface of the Earth. So when we consider statement 1, it says the Earth is not spherical but elliptical. Now what this teaches us is that because the Earth is not spherical but rather more like an oval shape, that tells you that the radius is different. When we pick the radius from the center here, the radius across this part here is going to be different from what you will get when you are considering the longitude and latitude. In mathematics, they call them the great and small circles, where we have the equator and then the Greenwich meridian and then the longitude and latitude. So because of this, acceleration due to gravity is different at all the points on the Earth's surface. So that tells us that statement 1, yes, is one of the reasons why the weight of an object vary. And while saying that, we've mentioned longitude and latitude, so that tells us that the variation in longitude and latitude also affects the weight of objects on the surface of the Earth. However, rotation of the earth on its own axis has no telling on the weight of objects. It does not affect it in any way. And the same way, variation in density of the earth also does not affect the weight of objects on the earth's surface. So the two correct statements there is 1 and 2. And considering the options provided, that will mean the answer is D. This question says, a satellite is in parking orbit if its period is. So quickly let us understand what parking orbit is and what period is. So starting with period has to do with the time taken for it to complete an oscillation. That is, if an object is going in circular motion or oscillatory motion and it starts here, the time it will take to complete this orbit is what we refer to as period. And then when we say parking orbit, now this is a temporary orbit that a satellite stays in, right, before it can then launch to continue its mission. So it is a temporary stable orbit for satellite to stay in. And when they are there, they are under the influence of Earth's gravity. So they tend to follow the Earth as it rotates about its own axis. So now, looking at those two now, let's find out which of these options would then be correct. So option A says that the period is less than the period of the Earth. B says more than the period of the Earth. And C says equal to the period of the Earth, while D says the square of the period of the Earth. Now back to this diagram. If a satellite is placed in this parking orbit, it means it's going to go around the Earth in the same time it will take the Earth to rotate about its own axis. So that tells you that the period of the Earth and that of the satellite has to be the same for it to be in a parking orbit. So the correct option is C. This question from UTME 2007 says, two spheres of masses 5.0 kg and 10.0 kg are 0.3 meters apart. So calculate the force of attraction between them, given that the universal gravitational constant is 6.67 times 10 raised to the power negative 11 Newton meter square per kilogram squared. So let's solve. The equation to use here is that F equals G m1 m2 all divided by r squared. So let's apply it. G, 6.67 times 10 raised to the power negative 11 multiplied by m1, 5.0 multiplied by m2, 10.0 all divided by r, which is 0.3 in brackets squared. So F here therefore becomes, now we can multiply this together. What we have here is 6.67 multiplied by, this would give us 50.0 all times 10 raised to the power minus 11. And then we divide this by, now you square this part, you get 0.09. So you can then finish this off using your calculator, and then F would definitely be 3.71 times 10 raised to the power negative 8. And it is measured in newtons. Now, of all the options provided, the correct one is option B. This question says, when a brick is taken from the Earth's surface to the moon, its mass, so we have to fill in this space. Now, one thing that we get confused with is the case of mass and weight. So I'm repeating this again. When you take the mass of an object, it is always the same regardless of time or place. It doesn't change. But weight, on the other hand, is affected by gravitational pull that it is experiencing. For example, the weight of a person on Earth reduced to about 1/6 of its value when that person is taken to the moon. This is because the moon's gravitational pull is about 1/6 of that on Earth. So you see how that changes, right? Based on the position that it is. So on the other hand, weight does not change. It is always constant. So get it straight. Mass is constant. Weight varies with the gravitational pull that it is experiencing. So the correct answer in this case is that the mass remains constant. So folks, we've solved some number of questions on this topic. You can also practice with many more questions that you can find on the Exam Fun app. It's an app that has been created to make your learning experience very fun and educative. So please download the app on Google Play Store, on the Apple Store. Register and continue to have fun as you learn. And also, please do not forget to share this video to all your friends that will be in need of this. The series still continues. This is just day 4. There's still many to come. So please share to as many. Let them also participate in this series as we go on to ACE Jamb Physics. And as always, do not forget to like the video, share, and subscribe to the channel. You can also click the notification bell icon so that you get alerted when the next video comes up. Thank you very much, and I'll see you in the next video.